This question, example 1, was find the volume of the solid of revolution obtained by revolving the region bounded by. And we did not finish it because we're gonna work on this today more and have more examples. So this is a whole long English phrase which basically says volume of solid of revolution, it's just a volume that is created, which is obtained by revolving some 2D region. Revolve 2D region, you get 3D region. This pocket is flat, and when I spin it, it becomes a 3D object. Kind of that's the idea. Now it's important new information. How do we revolve it? About what? About y equals x, about x equals 17, or about some kind of axis. So in this case, it's an easy case about x-axis. Step 1, sketch 2D graph, and then sketch 3D graph by rotating 2D graph. So that's typical like engineering job. So that's, I think engineers will like it, and physics majors. You sketch 2D graph by sketching those basic functions, y equals square root of x, x equals 9, and then y equals 0, that's x-axis. Then you spin it around, and it creates an object. Then you have to decide, so you first check how do we spinning it. We're spinning it around x-axis. That is always given. You don't decide on that. After this, you start the process of finding the volume of this new object. So next step. Step 2 and step 3, we rotated, we got 3D object. Step 3. Step 1 and step 2 are done. Step 3 is choose the case, just like we did with areas. Choose the case. Is it dx case versus dy case? Vs versus dx or dy case. So before, in areas, I told you if it's top minus the bottom, that's for case 1, dx, right minus left, dy case, which is second case. Here there are two ways to explain it, which is easier actually. Way 1 to explain it, you draw a sample disk. Again, you imagining you're a ninja and you're throwing disks at this object and slicing it, just like ninja would do. So you're slicing this object with ninja weapon, which is very thin, right? It's so thin that it's still barely you can see, but it has some width. So it's like that. But it's like a knife, so it's slicing them all. This is a sample disk. That's what we call it last time, sample disk. Like so. Where does the width of the sample disk maps? And maps, that's official terminology, maps or projects. Or how would you describe the width of this disk? With x or y? Well, I'm looking literally on the graph. Yeah, it's in the x-axis. The width of the disk is located on x-axis. That's how I know it's going to be dx case. Because width of the disk goes in the formula at the very end. This is where the width is. So if width is described with x-axis, then it's dx. With y-axis, then it's dy. So that's how I know that this case is a dx case. One more way to know it. That's a note. Let's do a note. Or let's do a note at the end. Let's do a note at the end when we finish the example. For the disk and ring method, if we're revolving about x-axis, then it's going to be dx case. So that's actually much easier. If you see we're revolving about x-axis or something parallel to x-axis, we immediately can say that is a dx case. Okay, so we chose case 1. Immediately write down the formula. It's not area anymore. It's volume. On the test, in your homework, when you don't have notes, right away you write down the formula, pi r squared. How hard it can be to memorize. Pi r squared. That's very good. Integral pi r squared. And now we agreed it's dx. Boom. Since we agreed it's dx, we know it's going to be from a to b, not from c to d. And the function of x is inside. That radius is a function of x. So this is already very important. You know the formula. Now you just need to figure out how to build this integral and then actually integrating it. But do you understand how we chose the formula? We have pi r squared, which is pi r of x dx, or pi r of y dy squared, right? So we chose it based on the logic I just explained. Now, check this out. V equals, kick pi outside because it's a constant. Now you have r squared dx. Before we do that, let's find a and b. A and b are x equals, x equals. This is where your 3D object is located. As you can see, I can describe 3D object taking physical space. It's 3D object. It's like a water bottle or a vase or a ball. It's either located from y to y, physically takes this space, or it's located from x to x. And this is when you choose the case. You choose how to describe it. So if you choose the x case, we're choosing to describe the situation using x values. So we're going to choose it from a, which is 0, to b, which is what? 9. Since we cut it, this infinite shape at x equals 9, now the shape is from 0 to 9. So it is from 0 to 9. This one was good. Finally, the last thing to do is, since we're talking about dx case, our function will be area between graphs. That is why we keep mentioning it. Area between graphs. Now it's kind of lots of written over here. So let me delete this, maybe this. And remind you, area between graphs is this yellow part. Here it is. How to describe this area? Top minus the bottom or right minus left? We already chose the case. It's case 1, it's dx. You're not going to do right minus left anymore. And if you don't know what I'm talking about when I'm saying top minus bottom, right minus left, it means you're very behind on your homework. Because it's due tonight, and it's a very, very important base of lots of knowledge. Area between graphs is extremely important in this class, and then in calculus 3 class, and then in differential equation class. Area between graphs seeds all the 3D, 4D, 5D knowledge. Because it's 2D, area is 2. So length of the interval is 2D object. Length of the interval, we learn it in school. How far from A to B, B minus A. Then this was 1D. When we go to 2D, now we have top minus the bottom, right minus left. And now we're going to do, in calculus 3, we're going to take it to 3D. Any kind of shape in 3D. Now it's going to be top minus bottom, right minus left, front minus back. So it goes in upper dimensions, and if you want to learn that, you have to be good at this right now. So this is important homework. I was very honest with people which homework is important and which one is not. So we're going to have radius calculated as top minus bottom. Top minus bottom. Radius of each disk is different. Look at the sample disk in green I draw. See the sample disk? This is big one. This radius will be big. And this radius is top minus bottom of the 2D object, the original one. Look at this last circle. This is the biggest one. It has the biggest radius, also top minus the bottom. Look at the first one. It has 0 radius, then a tiny radius, and so on. The most important that since the radius is different from disk to disk, the radius is a function. And this function depends on the location of the disk on the x-axis. If disk is at 9, then the radius is big. If disk is at 0, the radius is 0. If disk is at 2, then the radius is different. That's why the radius is a function of x in this case, or of y for case 2. R is r of x. That's how we write down if we want to make a point that something is a function. And it's going to be area between graphs. Area between graphs or curves, graphs, which we learn in 7.1. 7.1. In this case, top minus the bottom. Top minus bottom. Go back to the 2D graph and check which function is at the top and which function is at the bottom. There should be y equals blah, blah, blah. Y equals blah, blah, blah. Top minus the bottom. Who can tell me? Square root of x minus 0. Let's check carefully. I was good last time and I signed each function. Check this out. Very proud. This is the top function, y equals square root of x. And the bottom function, they actually called it x-axis. And this was the reason why I asked you, how do we call x-axis in terms of function notation? Expression. Y equals 0. That's why we need it. This is y equals 0. Y equals 0. And now you know why it's important. Because we're going to have top minus the bottom. Top minus the bottom. Square root of x minus 0. Square root of x minus 0. How about the square? Why I'm squaring it? Pi r squared. Exactly. This thing in yellow, only in thing in yellow, not the squared. That's the radius. So r equals, and since we have formula pi r squared, we're going to square this radius. So you see, radius is the area between curves, area between graphs, and then we put it in the formula pi r squared. Make sense? Top minus the bottom, or right minus left. Boom, this is pretty easy to integrate. We're going to have pi is outside from 0 to 9. Square, let me write down, square root of x squared dx. In some books, you will see square root of x right away, but I'm teaching it better than that idea. It's top minus the bottom, because later they make it more complicated and it shows up out of nowhere, top minus the bottom. It's always been there. So I do tell you that my notes are better than what they show in the book. I checked. And that's why many students got confused, including me when I was learning this. Top minus the bottom right away. It was there all this time. It just somehow shows up later in the book. I don't know why. So it's going to be pi. Did you finish integrating? Or are you waiting for me? X dx pi x squared over 2 from 0 to 9. Plug 9, plug 0. Subtract, and you will get 81 over 2 pi. You better have a positive answer because it's area. It is, oh, it's not area. It's volume. Units what? Cubed. You better have positive answer. It's like, it's an object. It's volume of the vase, of the water bottle, of the drum you're playing with, and so on. Just to make it beautifully explained one more time, let's write it down. Pi r squared is area of the disk. Area of the disk, I will skip the or a, just area of the sample disk. Pi r squared. Pi r squared. And dx is the width of the disk. Width of each disk, and they're all the same. So area depends on r, while width is all the same. And now we're summing them together. Remember that integral, the whole idea of integral is a fancy summation. What kind of summation? With limiting, with infinite number of whatever we're summing. So integral is a fancy way to sum up things. So we're summing up all those disks. You were ninja, you were slicing this 3D object, and you end up to have those slices. You add them together, infinitely many of them, it gives you exact volume. Make sense? So this is how integration looks like. It just sums up infinitely all of these disks. What do you think? Not too bad? Questions, ideas, suggestions? Second example. Still keep thinking about it. You can always ask questions after. I'm always happy to go back. The second, find the volume of the solid, blah, blah, blah. Find the volume of the solid of what? Evolution? No, revolution. Okay, if you skip R, it becomes evolution. I just realized. Revolution obtained by. Okay, it's very tiring to write down it every time. Obtained by. So this is going to be the last time I'm writing down all this long phrase. The most important is happening after obtained by revolving what? By revolving. Revolving what? The 2D region. So people just say region. BDD bounded by. So you see, this phrase is the same every time. So as a mathematician, I scan this through, especially as an English as a second language person. I scan it quickly, and then I just find what is my favorite part in this are formulas. 2 over y, x equals 2 over y equals 2, y equals 6, and then y-axis. So that's how I was learning. When English is your not even second language, but third language and so on, this is lots of words. Mathematicians, we don't like when it's lots of words in problems. We like the less words, the better, to be honest. So this is, of course, for engineering and physics department. They created these ideas. So when I was learning all of that, of course, I learned it with the way, the less I read, the less confused I am. So I learned what is repetitive and what is important, and now I'm teaching it this way, which is very helpful for international students and English as a second language students, ESL students. We have lots of Hispanic students in our classes, so definitely it's very nice to know. Just scan this all really fast and find the important part. Something is missing. Did you guess what? Rotation, exactly. Rotating about what? And that's a new information. We cannot create a 3D object if we don't rotate this 2D object. This time it will be about y-axis. It's not equal sign, it's y-axis. Solution. So now you know. I know that I need the equations. Here they are. And then I need the rotation information. And it's not always the axis, you should know. So it will be something else in the future. Solution step 1. Sketch the 2D graph and then rotate it. What do we have in 2D? 2D graph. And just make a sketch. You don't have to be precise. But that comes from the 7.1 chapter, which is area between graphs. How good you are in sketching things, especially fast. You guys have graphing calculators, but in general, I do it because I learned graphs. People, don't get distracted, please. Don't get distracted. So, let's do it. What is the easiest one in the list? The y's. Y equals 2 and y equals 6. I will do it later because it's a slice. I will do x equals 2 over y. X equals 2 over y can be rewritten as y equals 2 over x, right? And we had this function before. It's something like this, blah, blah, blah. I will just keep this one. Then I have, it is infinite, as you understand. So we have a 2 cuts. Height y equals, so let me write down, x equals 2 over y. Then we have a slice. It's not a slice, it's a cut. Y equals 2 height. Make your y taller. And then we have y equals 6 cut. Let's make them the same color. Do you see the 2D object created? Here's the area bounded by, or enclosed by. So there's lots of English synonyms you'll see in the homework and in the book. Enclosed by, region enclosed by, bounded by, restricted by, and so on. Region, area, blah, blah, blah. Now we need to read how do we revolve it. We're revolving this about y-axis. So American Annotation does this little wiggly thingy, which I like. That gives me good notes in the future. How did I create this 3D graph? By revolving something about y-axis. And now I taught you last time, look at the y-axis as a mirror. If you're good in art, you do it better than me. But it's interesting that there's some kind of logic about how do you actually draw things in 3D. So people who like drawing right now, probably enjoying this a lot. See the y-axis as a mirror. Copy what you see just for the 2D region, like so. Okay, copy it. And then it doesn't look like 2D object. So for your brain to justify that it is a 3D object, maybe put 2 circles. I usually put one at the top and at the bottom, or maybe sometimes even one in the middle, like so. Now it looks like a 3D object. Looks like what? Can you have any suggestions? How do we call this object?
Lampshade.
Lampshade, what else it say? Volcano is popular idea. Although volcano has a hole inside, and we're gonna have this example today. This one doesn't have, this one is solid, so it's a solid volcano. Very good one. Anything else? Yeah, good enough. So some kind of 3D object that looks like this. Let's find volume of this 3D object. Step 1, 2D, step 2, 3D, done. We did those 2 steps. Step 3, choose the case. Case. So I explained a hard way to know the case and the easy way to know the case. The hard way, you create a sample disk. You're slicing this object this time horizontally. So it's going to be a horizontal slice. Here are my horizontal sample disks. How to describe the width of this disk using dx or dy? Dx, it's like over here on, oh sorry, dy, you're right. Dy case. It's exactly on the y-axis. Yeah, don't question yourself. If you're right, you're right. You should question everyone else. Be confident. So it is a dy case because the width of this disk is located on the y-axis and can be described with the height versus x-axis. Also, you can say that it is a horizontal slicing. Horizontal slicing belongs to case 2. But I never remember those phrases. Too much to memorize. All this English phrases, too long also. But you can see it is horizontal. It's lying down. So students told me the easiest way they remembered, if you're revolving about y-axis, that's dy. That's it. Simple as that. But this works only for this chapter. For the next chapter, it will be reversed. So dy case, for many reasons. The width is on the y-axis, dy, and it's revolving over y. It's also dy case. So case 2. Or dy case. Let's just keep it as it is. Dy case. Okay, so now you can write down the formula. Volume is, who can scream the formula? Very complicated formula. It's pi r squared. Yes, complete. With integral, please. R squared, what is at the end? Dy. Good job. From C to D. That is our formula for case 2. See, people left the class and actually wanted to give you a very funny pun today, which is going to happen in a sec. I have a pun. I prepared a pun. I know, right? I'm like, no, please no. So this is going to be case 2, which means R depends on Y. And C and D are also on y-axis. Let's create it. First we're going to create where does this object located on y-axis. You see, I could describe this object from minus whatever this, minus a to a, right, whatever. But we chose case 2, so we're not going to do that. We're going to describe this object on the height level, how high this object versus the previous 3D object we described was how wide it is. So, but it's so cool. We again have 2 slices from where to where this object is located. From 2 to 6, exactly. How cool is that? We sliced it so conveniently, and that's why the case was a good case. If you had to do from this point to this point, you actually have to find those points. So it's nice. From 2 to 6, now I will have function minus function dy. Let's put it in black. Dy. Whatever is inside will be area between graphs. Area between graphs. And now we have case 2. So what kind of situation do we have? Top minus the bottom or right minus left? Right minus left. Amazing. Right minus left. Very good, people. I'm kind of glad that's people saying something. I like when people saying something. It's nice to hear some feedback. Right minus left. Let's go back and see who is on the right and who is on the left. We only look at the 2D area. So some people draw it separately. I don't like drawing it separately. Here it is. This is my 2D area. Which function is on the right? I even sign it. X equals 2 or y. And which function is on the left? Did I ever mention that we have y-axis? How to call y-axis? X equals 0. See? So we have, and it's supposed to be x equals x equals. That's important. If it's not x equals, you'll have to find it for x. X equals 2 over y minus 0. That's how you create it. Simplify, integrate, and you got your stuff. Does that make sense? It's going to be pi from 2 to 6, and you have 2 over y squared, dy. Square it, integrate it, and you have 4 pi over 3. 4 pi over 3 units cubed. Check by yourself, it is correct. So building the integral is extremely important. On a test, we're going to give you multiple choice questions with 5 integrals. You have to choose the correct one. And the one we actually have to build. What do you think about this? Think about 2 questions. Do you have any 2 questions?
Are there scenarios where like graphs kind of overlap or they like cross and then a new graph becomes the top and a new graph becomes the bottom?
Yeah.
And you have to like do 2 separate.
Very good question. We had it in the homework when graphs exchanged location. One was on the top and become the bottom and so on. Whatever you're going to rotate, that's going to be the 3D object. Whatever was at the beginning, that's going to be your 2D object. So yes, since you had it in 2D, when you rotate it, it becomes 3D, and you'll have to deal with that. Yeah, but it's a pretty hardcore case, though. Good question. More questions? What is happening if... Oh, so maybe let's... Okay, I will do it at the end. What is happening if we're going to have this rotation, but shift it maybe a little bit to the right? What if we had the same function y, x, let's see, x equals 2 over y, here it is. We have the same shape in 2D, here it is. But instead of rotating about, oh, it's a bit different. We had the same shape in 2D, that's what we just had. But instead of rotating about y-axis, we're going to rotate about something different, like this. X equals minus 1. Then, if we're rotating about something else, we're still mirroring everything. Rotate, and that creates a tube inside. That means some 3D objects can have a hollow piece inside. Hollow piece means empty, and we need to learn how to find volume of that. Very cool idea, very logical idea. We're going to find the volume of the whole thing, pretending it's solid. And then guess what? Subtracting the hollow piece. The hollow piece in this case is a tube. Find the volume of the tube, subtract it. So it's pretty amazing, very clear idea from engineering point of view. I'm going to call it a washer method. Washer method. So this chapter 7.2 is called disk and washer methods. A washer method, which basically has a shift. Shift can be a bit different. You'll see that shift for the rotation or shift of the location of the original function, but anyway. So let's do that. Washer method is called washer method because it will be using not disks anymore. Let me show you that. Disk, like a ninja disk, looks like this. It's filled in with a tiny width, right? Like so. And you're slicing it's like that ninja object, like super dangerous, like a knife. Versus a washer. A washer is this disk with, guess what? An empty part inside. And they both have width. The outside part has a width and the inside part has a width. So I thought for a while as a foreigner that they mean only American book called a washer. So I thought for a while that they mean a dishwasher, because dishwasher is a tube, right? With a hollow piece. Guess what it means? It's not the dishwasher. It's washer from the tools. I just did not know that thing called a washer. That's upsetting, but it's a fact. Like only a year ago I learned that. So this is a screw, right? That's a screw, right? And then this is a washer. It goes on the screw. Duh. That's like, I didn't know that for a while. And that's why I don't like calling it a washer. In some books they call it a ring, and I like it more. Because a ring, I can imagine what it is. A ring can go on my finger, so obviously it has an empty part inside. So we're gonna learn how to use rings to approximate things. If you have different sizes of rings, but they're all circular, and you map them on top of each other, you will create a vase. That just makes sense. If you now put those rings on top of each other, inside they will be hollow. So they create an empty vase with the place for water and so on. What will be the difference in the formula? The difference in the formula will be, let me see if I have a beautiful one. Yes. V, volume for the washer method, is going to be integral from a to b. It's still a of x dx or a of y dy, where a is the area of the washer and dx is a thickness of the washer, right? Area of the ring. I like it called ring because also it's short to write down. So volume will be integral from a to b. Now we will do this thing. It's going to be, remember this phrase. So if you zoned out for a second, this is a good moment to like check in back, like sign in to this class one more time. This is a good moment. Pi r squared minus pi r squared. Pi, capital R squared, minus pi small r squared dx. This is what you should remember. Guess what does the first pi r squared means? Volume of what? Area of the whole thing, the filled in one. So we call it solid or filled in, right? Filled in part. So we pretending there's no hollow piece inside. There's nothing empty inside. And then we're subtracting the empty part. Empty, or you call it hollow, right? So it makes sense you have filled minus empty. That's what we're doing it. Filled, maybe like so, empty. I like it this way. You fill it in with a liquid, pretending it's all filled in, and then subtract the liquid. That's exactly visually how I see it. And now you have two cases, obviously. Obviously, you have two cases. Case 1, that's dx case. Case 2 will be exactly the same thing, but instead of r depending on x and r depending on x, pi r squared minus pi r squared, you will have integral from c to d, pi r squared minus pi r squared dy. Each r depends on y. Depends on y. Case 2. And the logic will be exactly the same. If it's rotating about x-axis is the x case, about y-axis is the y case. Washer method. So, interesting. Do I have it here? Ooh, look at that. I do have it here. Copy it for you. This is from your homework. Apparently, it's number 12. Okay. With a shift. I don't know if I want to do the shift right now. Let's see the integral. No, it looks good. Yeah, let's have a shift. So, this is number 12. Washer method number 12. Before, do you have space? Did you leave any space here or not? I guess no. I'll do the note at the end. The note at the end will be rotation idea. If it's rotating about x-axis or anything parallel to x-axis, that's the x case. If it's rotating about y-axis or anything parallel to y-axis, that's the y case for the disk and washer method. So while you're writing down the problem, find the volume forward by rotating the region enclosed by y equals 6 squared of x, y equals x, and y equals 36. So we're rotating about not x-axis and not y-axis. And that is when we know it's going to be a shift. A shift. Let's make this huge note. So put it in some kind of bright color. I will make this note above. But now we are ready to summarize. If you rotate, or rotation happens, I don't want to write lots of English. If rotate about x-axis or anything that's parallel to x-axis. This double line is a sign for parallelity. Do you remember that? Parallel. If rotate about x-axis or anything parallel to x-axis, then this is the x case. If rotate about y-axis or anything parallel to y-axis, then it is the y case. Only for disk and washer methods. So for disks and washers, and we're gonna flip it for the next chapter for shell method. That's why it's important to know. But for now, it's pretty straightforward. Before we had rotation about x-axis, that was the x case. About y-axis, dy case. Now we're rotating about y equals 36. Guess the case. It's like 50-50. It's either first one or second one. Which one? Dx. But it's y equals 36. Why not dy? You need to figure out which this line parallel to. Is this line parallel to x-axis, parallel to, or it's parallel to y-axis? Well, if you draw it, y equals 36 is vertical. So it's parallel to x-axis. So you were right. It is actually the x case. That's how you know. Does it make sense? Pretty cool idea. Pretty cool idea. Let's sketch the graph. So, the graph in 2D first. The graph in 2D. Solution. Just make a sketch. Again, you don't have to be perfect or beautiful here, but have enough space because we're now rotating about some kind of line which is parallel to x-axis. So have enough space up and down, also left and right. Y equals 6 squared of x. We kind of keep having this function all the time, just with different numbers. Y equals 6 squared of x. What function is that? How to draw it? Who remembers? We had this kind of, let's see if that is the correct one. Let me, oh, I see, it's a different problem. I will do y equals x first. That's the easy one. This is the symmetrical cut. Y equals x. Y equals 6 squared of x. Square root of x looks like so, and then times 6 is just increasing or decreasing faster. It's stretched or shrinked. Y equals square root of x. Oh, this is already a region, you see? And that's why they did not give us thousands of lines like last times. It's already a region. Here it is. Now, how do we rotate it? Let's check it out. Very interesting. Don't draw anything right now, but check this out. If I would rotate it about y-axis, then it would look like so, and then we have this rotation, right? Pretty cool. It will have a hollow piece inside. If I would rotate it about x-axis, like so, then I will also draw this line, see? And it also creates a 3D object with a hollow piece inside. So you see, we're gonna have those cases quite often. But we actually rotating about y equals 36. You need to decide if this line y equals 36, crossing it or not crossing it, smartly enough, it is higher than the whole object. So I need to actually move this picture down. How do I know? What if it's like over here? Is it? So I'm gonna draw y-axis quite high. How to know? Who can guess?
The two curves intersect lower than 36.
This is what's this number? Can you figure out? This point of intersection, 6 squared of x equals x. Squaring, 36x equals x squared. 36x minus x squared equals to 0. Factor out. Square root of 36 minus x equals 0 and x equals 0. So you have 2 points of intersection, 0 and 36. Exactly. So when I'm saying that I'm rotating at line y equals 36, it is actually Exactly this line. Am I correct or not? What do you think? Is it correct? Good. So this is going to be my line of rotation. Y equals 36. How to do it nicely? How to do it nicely again? You see it as a mirror. You're nicely copying everything, which is there was a curly piece inside, then the line outside, and then draw at least 2 circles to see what is going on. So this is what is going on here. You need to choose the case. So we're almost done, people, almost done. 5 minutes. 2. 3D graph is done. Check mark, check mark. 3, let's choose the case. We already chose it. Since it's rotating about the line, it looks like x-axis. It's literally parallel to x-axis. This is the x case. Finally, let's build it. Volume is integral from a to b, and we already know a and b. On x-axis, a is 0, b is 36. Is it? Oh, that is exactly what my question is. This picture is not correct. I was thinking, why it doesn't look correct to me? Is it correct or not? So the input is 36, but what is the height?
It's actually still 36.
Oh, it's still 36, just because it's multiplied by 6. Okay, then it's fine. Y equals 6 square root of 36. So it's not 6 after all. Yes, okay, good. I was concerned about this. So it's going to be from 0 to 36, pi r squared minus pi r squared dx. This is the formula we're using here. And now it's going to be the hardest part, is actually to figure out the which one is which. How to build one in terms of another one. I will build it right now for you and explain it in more details on Wednesday, because I do think people will get confused. I kick out pi outside because it's pi r squared minus pi r squared. Integral from 0 to 36. Capital R is the radius that is pretending everything is normal and it's filled in object. So I'm building this huge slicing disk. And check which graph is on the top and which one is at the bottom. The graph is on the top is this line over here. And the graph is at the bottom is actually y equals 0. So that's going to be my first function, r squared. Y equals 0. And the smallest one will be, I'm now building this small disk that is only describing the empty part. Check this out. For this function, the function at the top and the function at the bottom are different. And I would say I would leave it and describe it better next time, because it's too much to work. So one more thing I wanted to mention. Before you have questions, you can definitely ask me questions about any of this. But I wanted to mention a pun. The highest level of knowing English, I believe, is to learn puns. Because puns require knowing of language, local culture, and sense of humor. And it's hard, especially you guys mixed up the words. So my favorite pun is, I will tell you, what is the favorite pirate's letter? What is pirate's favorite letter? No, it's not R, it's the C. Right, that's my favorite one. I'm very proud that A, I memorized it, B, I understand it, and C, I can recreate it. Now you know it, now you know it.